Okay, gang, here we are. Today is a little bit of a strange day. So my son got very sick over the weekend. We had to take him to the ER. It's been a big mess. He has a pediatrician appointment this afternoon at 2 p.m. So rather than doing our normal live lecture, what I'm doing is pre-recording a lecture for you now. It's about 1 o'clock, which means that we won't be doing the normal live lecture thing today. So I'm going to set this to upload before I leave to go to the doctor's appointment and do my best to get to you as much of the information that you need to continue on your homework path as possible. Last week, we talked a lot about calculating limits of functions using the graph of a function, and that's a really useful skill. Not just because oftentimes you will do that, but also because it helps you kind of understand what a limit is compared to the value of the function. We talked a bunch about that in class, right? The limit doesn't care about the value of the function at that input. It cares about the behavior nearby. So limits are looking at what is this function doing as you get closer and closer and closer and closer to this particular x value. Then whatever happens at that x value could be anything, right? You could have an open hole here and a filled in point somewhere else. Limit doesn't care. You could have an open hole here and no filled in point anywhere at that x value. Again, limit doesn't care. We talked a little bit about how to connect that to the algebra that runs in the background. What I'm going to do today is show you just the basic limit laws. So the kind of algebra of the limit operator. This is thankfully a pretty quick lesson. It's not something that really requires the full 75 minutes that we have allotted to our lecture time. So if we had to pick a day to do this, this ain't the worst day. I'm going to pause the recording for just a second because I'm getting a call from my wife. Okay, we're back. So title card, this is MAC2311, section 004, which is a Calc 1 class kind of meeting on the date 1/10/2022. The topic for today is limit laws, which is section 2.3 in your textbook. Essentially what these are some rules that tell you how the limit operator plays with the algebra operations that you know, like multiplication, division, addition, and subtraction. I'm just going to give you the theorem. All right, and I'll show you where this is in the textbook. All right, it's right here in section 2.2, section 2.3. This says under certain conditions, right? C is a constant and each of these limits exist, then we can do the following things. Stop following me. You ever just have one of those days where the phone won't stop ringing and shit just won't stop going wrong? This is one of those days. Okay, section 2.3 is all about calculating limits using the limit laws. And the good news is that this shit all goes exactly how you would hope, meaning the limit operator kind of commutes with all of the algebra operations that we use. So you see here, assuming that C is a constant and the limits as x approaches a of f and the limit as x approaches a of g both exist, then the good news is everything you want to be true is true. Namely, the limit as x approaches a of a constant times your function f of x is the same as the constant times the limit as x approaches a of f of x. I'll label these as 1. 2, the limit of a sum or difference of functions, lim x to a, f of x plus or minus g of x, will be the sum of the limits of f of x, or the difference of the limits. And the same thing is true of products and quotients. So the limit as x goes to a of the product, f of x times g of x, that is the same as the product of the limits. And finally here, the limit of the quotient is the quotient of the limits. So if you have the limit as x approaches a of f of x over g of x, that's the limit of the top divided by the limit of the bottom. All right, so this is the theorem on your limit laws. We can actually extend this quite a bit. Oh, this is as long as the bottom, x to a of g of x, is non-zero, right? This can be extended a little bit more. We can also say that the limit as x approaches a of f of x, all here raised to some power, constant power c, that is the same as what you would get if you took the limit inside and raised the whole thing to the power c. So basically, limits commute with all of the algebra operations, as long as the limit of whatever the pieces are exist. So if you're given some big expression and you're asked to take the limit of it, you can take the limit of each piece individually. Before we go into examples on these, and I will show you a few examples, I want to come back to the hypothesis here, and that is that the limit as x approaches a of f of x and the limit as x approaches a of g of x both exist. Remember last week we talked about some criterion that tell you whether or not a limit for a certain function at a certain x value exists or does not exist. The big thing for us was that the left and right limits have to be equal, right? If you approach from the right, approach from the left, and you get different values, then the overall limit there does not exist. There's one other way that we're going to encounter that these things can go quite badly wrong. So before I go into examples here, I just want to confront one other possibility. And I believe you were introduced to this in your homework set, but a note on rapidly oscillating functions. All right, it is possible. Let me look at the example here. F of x equals the sine of 1 over x. It is possible that a limit fails to exist for a reason other than having left and right limits not being equal to each other. The graph of this function is pretty tricky to draw. And to help you get an idea for why that's the case, before I draw it, I just want to talk a bit about what the inside of this function does. So 1 over x is a graph that you should know, right? It's the hyperbola. Near 0, 1 over x gets really big. We talked about limits at infinity before. Here, I'll sketch y equals 1 over x over here. Sorry, limits, infinite limits before. We talked about those on Friday of last week. And as x goes to 0 from the right, 1 over x goes to positive infinity. As x goes to 0 from the left, 1 over x goes to negative infinity. What we're looking at here with this function f is 1 over x tucked inside the sine function. And you know, as the inside of the sine function gets bigger and bigger, sine just wobbles back and forth from -1 to 1. But how fast it wobbles depends on how quickly the inside function is growing, right? The sine of 2x wobbles faster than the sine of x. The sine of 3x wobbles faster than the sine of 2x. So as the inside of this guy gets really, really big, which does happen as 1 over x as x goes to 0 here, as the inside function here gets really, really big, the sine function starts to wobble back and forth really, really fast. And that sort of rapid oscillation can also destroy the existence of a limit. So what I mean is, if you look out here, this looks more or less like a regular sine function. Goes up to 1, goes down to -1. But as you sneak in closer and closer to 0, he starts oscillating faster and faster and faster to the point where he becomes, the words are dense in the plane. If you look anywhere just to the right of 0, on that interval from 0 to that number, say from 0 to 0.001, this function will have bounced back and forth from -1 to 1 infinitely many times. And it does that on the other side here as well, right? He oscillates insanely rapidly, and then as you go out, he starts to calm down again. So this sort of behavior, this is bad news. My ability to draw such a function's graph is limited, right? Because I can't draw infinitely many oscillations in here. I have finite amount of time to do so, but Desmos can help me. So if we take a quick peek at this guy, here he is. And you see, like I said, reasonable speed oscillations out here. But as you get in towards 0, 1 over x gets very, very large. And that means that the sine of 1 over x begins to oscillate very, very fast. Maybe I can turn down this boldness. It's already turned down as much as I can. So as you zoom in here, you see this guy bouncing back and forth, up, down, up, down, up, down, up, down, up, down, up, down, so fast that basically the whole y-axis here near 0 is just red, right? Not just the y-axis, but everything within epsilon of the y-axis. It's just like a red block. So we have to ask ourselves, does the limit as x approach 0 here exist? Does the limit as x approaches 0 of sine 1 over x exist? Now, based on me calling this bad news, you might guess that the answer to that question is no. And that's correct. The answer to this question is no. The reason, remember, what we're asking here is it the case that as x gets closer and closer and closer to 0, the y values on this graph get closer and closer and closer to some fixed number? The answer here is no. Because as x gets closer and closer and closer to 0, which is what this notation means, it is not true that the y values on the graph, in other words, f of x, gets closer and closer to any fixed value, any fixed y value. It just bounces back and forth faster and faster and faster and faster as you get closer and closer and closer to 0. This is something that you saw in, I think, one problem on that last homework set. And WebAssign does a reasonable job talking about why that limit doesn't exist, but I wanted to spend a second talking about it here. So as long as you don't have something like this going on, or one of the violations we discussed last week, like the left and right limits being non-equal, then those limits do exist. And as long as f and g both satisfy those conditions, you can play any number of these games when you're asked to take a limit of a combination of f and g. All right, let's take a quick peek at an example problem or two. So you see in this first example, the graph of the function f in pink and the graph of the function g in blue. I'm going to sketch this. And then we're going to calculate the requested limits. I don't have pink here, so I'm going to use a purple in place of pink for the function f. Okay, so come out here, 1, 2, 3, 4. And to the left, 1, 2, 3. Okay, and the function f does this. And then dipping back down to and then coming back here. Oh, it's supposed to be, okay. Okay, so something like this for our function f. Sorry, I'll tab back over in one moment. And then our blue function is just screwing off over here. And here we go. Okay. All right. So what we'd like to do is calculate, sorry, let me get these limits written down. The limit as x approaches -2 of f plus 5 times g. Let's see if we can work this out. Okay. So what we want to do in order to sort out this limit from this graph is apply our limit laws. And applying those one at a time, here's what we get. Our first limit law says if you have a sum of two functions and you're trying to take the limit of that, then you can take the limit of each part of the sum. So that's the limit as x goes to -2 of f of x plus the limit as x goes to -2 of 5g of x. That's using the first limit law. I'm sorry, second limit law? Second limit law, splitting up the addition. And then the first limit law can be applied to this second piece. Leave the first piece alone. X goes to -2 f of x plus 5 times the limit as x goes to -2 of g of x. All right. So here we're using the rule that says the sum limit of the sum is the sum of the limits. That's rule 2. Here you're using rule 1 only on the second piece. That says a constant multiple inside here, 5 times g of x inside the limit. That constant can pop out. You get 5 times the limit of g of x. Now we look at our graph. F is in purple. G is in blue. And I want to try to figure out the limit as x approaches -2 of f of x. Well, -2 on my x-axis is right here. So you imagine a little dude walking closer and closer to -2 from the left or from the right with his feet glued to this graph. His y values are getting closer and closer to +1. So this first piece here is +1. And then we have our plus. We need to figure out the limit as x goes to -2 of g of x. Now, g of x is the blue graph. So here near -2, what is this guy? Well, he doesn't have any holes or any weirdness. You can imagine walking along the graph, getting closer and closer to -2 from the left or from the right. That value is -1. So this 5 comes along for the ride, and we have times -1 here. In other words, the limit as x goes to -2 of f is 1. The limit as x goes to -2 of g is -1. So this plus 5 times that is 1 plus 5 times negative 1. And then it's just an order of operations thing. This is 1 minus 5, which is negative 4. Let's look at part B. Part B, we want the limit as x approaches 1 of f times g. By our third limit law, this is the same as the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. So we use our limit law to split this limit up, and now we will look at each of these individually. Let's look at f first. Again, the purple graph is the graph of f. Here is x equals 1. If I'm a little dude with my feet glued to the graph of f, as I walk towards x value 1, my y value is going to 2 from the left. And as I walk towards having x value 1 from the right, my y value is also going towards 2. So this limit is 2. G, on the other hand, is not so well behaved near 1. If my feet are glued to the blue graph and my x coordinate is getting closer and closer to 1 from the left, that means I'm walking along like this. So the left limit here is negative 2. But the right limit here, as I get closer and closer to 1, there I'm going to negative 1. So the second guy is a DNE, and that's because the limit as x goes to 1 from the left of g of x is negative 2, but the limit as x goes to 1 from the right of g of x is negative 1, different values. Okay, I know this is a little bit difficult. I keep getting these interruptions, but that's how it is today, is chaotic. So we have 2 from the first limit, and we have DNE from the second limit. And this is not a product that you can form, right? 2 times something that does not exist, that's a very difficult multiplication to do. If either of these do not exist, then the overall limit does not exist. And that's the result here. Let's look at one more of these. We want the limit as x goes to 2 of f over g. And according to our limit laws, we can calculate this by taking the limit of the top and dividing it by the limit of the bottom. So let's look back at our graphs. As x approaches 2, what does f do? Well, f is the purple graph. 2 is right about here. It's hard to say, right? It looks like it's somewhere between 1 and 2, maybe 3/2 or 1.5 would be a reasonable guess. But if you look at the graph of g, he is going to 0 as x approaches 2. So the top here is maybe 1.5, but the bottom is 0. And that's a problem as well, right? We said we can only apply that limit law as long as the bottom is non-zero. So in this case, the limit would not exist again. Now it would come out to some flavor of infinity, depending on whether you're looking at the left limit or the right limit. I can be really specific about this. The limit as x approaches 2 from the left of g of x, my function downstairs, is going to be 0. And we approach 0 in a negative fashion, right? So imagine you're just to the left of 2 along the graph of G. There's my dude. His y value is very close to 0, but it's negative. And there is a notation for this. We would say 0 minus, like that. So g of x is going to 0 in a negative fashion as x approaches 2 from the left. If you were to be approaching 2 from the right, g of x, just that denominator, again, coming in here from the right, I'm going to 0, but I'm going to 0 in a positive fashion. So this would be denoted a 0 plus. So overall, this limit we would say does not exist because the overall limit of that ratio, lim x to 2, f of x over g of x, when taken from the left, the top is going to something like 1.5. The bottom is going to 0, but is negative. So if you take something very close to 1.5 and you divide it by something negative, but very close to 0, you have a positive number divided by a negative number. We could say this is 1.5 over 0 minus, and that would be negative infinity. Remember the mnemonic we had last time, that like a number over 0 is infinity, but it's a little bit subtle because it depends on whether you're talking about positive or negative. That same thing is going on here. On the other hand, if we look at the limit as x approaches 2 from the right of f of x over g of x, the top is still going to something like 1.5, but the bottom is going to 0 plus, right? Very small but positive number. And so this would give us positive infinity. I'm going to pause here. Okay, so this is where we're left off, right? Just with that first example, we calculated these limits using the limit laws and these graphs. We were able to split up this sum and then pop out this constant. And then since each of these limits existed, the overall limit existed, and we were able to calculate it as the combination the limit laws suggest. The other two limits in this example turned out to not exist. In one case, because the limit of g of x at 1 did not exist. In the other case, it was due to the ratio. We had the downstairs going to 0. And while that is not always a death sentence for the limit, it does mean that the limit is at best infinite, either positive infinity or negative infinity. But in this specific case, the downstairs went to 0 in a negative fashion from the left and in a positive fashion from the right, meaning the limit of that ratio as x goes to 2 from the left was negative infinity, and the limit of that ratio as x goes to 2 from the right was positive infinity. And we've seen in the past that if on one side you get negative infinity and the other side you get positive infinity, the overall limit there would not exist because negative infinity and positive infinity are things we think of as different numbers. There is more to talk about here, and unfortunately, I have to rush off to my son's pediatrician visit. So what I'm going to do is share with you just one more little fact or set of little facts that I think you will find useful. Essentially, what this theorem says is that there are a handful of limits you can calculate just by plugging in. If P is any power, then the limit as x approaches a of x to the p is just going to be a to the p. There's one exception to this rule, right? And what we're saying here is that you can calculate this limit just by plugging in. The only exception to this rule is if p is negative and a, the place you're taking the limit of, is 0. Because of course, if p is negative, then this is like 1 over x to some power, and you cannot plug 0, excuse me, cannot plug 0 in downstairs. The other rule is that if c is a constant, then the limit as x approaches a of c will always just be c. And there's no addenda here. This is just true full stop. This is broken down slightly more granularly in this portion of the book here, page 96. This is the extension that I gave you earlier, and we said this is actually true regardless of whether n is an integer or not. A special case of the version of this that I just gave you here is this, right, number 8, the limit of a constant being that constant value we gave you, and this is kind of a consequence of 6 and 8 put together. This is also a consequence of one of the things we said earlier. So the upshot here is that if you have a rational function or a polynomial, then you can calculate limits just by plugging in. And I'll go ahead and state this as a separate theorem. If f of x is any polynomial, then the limit as x approaches a of f of x is just what you get by plugging in, right? You plug in the value a for x. We could also say if f of x is a rational function, p of x over q of x, where p and q are polynomials, and q of a is non-zero, then the limit as x approaches a of f of x, again, is what you get just by plugging in. This section is not terribly exciting. In fact, I bet all of these things are things that you guys would assume to be true if we didn't tell you they are true anyway. But it is worth thinking about because we're going to talk a little bit in detail about how these things can go wrong, and that's an important thing. I remember what we said last week. This is the definition of continuity. So we're not saying it yet, but polynomials are continuous, and rational functions, likewise, are continuous everywhere except where the bottom is 0. Okay, we can take a quick look at an example here. This is fine. Let's look at something like that. Okay, so example, find the limit as x goes to 2 of x cubed plus 2x minus 1 over 3x minus 2. This is a rational function. It is a ratio or fraction where the top and bottom are both polynomials. So all you need to do is check that the bottom isn't 0 when you plug in a, which in this case is 2. As long as that's true, then you can calculate the whole limit just by plugging in 2 for x. And be aware this isn't going to work for most of the limits we calculate in this class. But the point of this section is to drive home when you can do this. And the answer is really anytime the expression makes sense, as long as the bottom isn't 0, or as long as you don't have a negative under the radical, all of that stuff. So 3x minus 2, if I evaluate this at x equals 2, we get 3 times 2 minus 2, which is 6 minus 2, which is 4, which is not 0, which, according to this theorem here, means I can take this limit just by plugging 2 in for x everywhere. So I'm going to get 2 cubed plus 2 times 2 minus 1 divided by 3 times 2 minus 2. Now that bottom we already calculated, that was 4. The numerator here is 8 plus 4 minus 1, which is 12 minus 1, which is 11. So this is 11 fourths. Not terribly exciting stuff, I confess. But those limit laws, these statements are statements with which you should be familiar. Right? These are important. So I apologize. I do have to cut this short and run off to the pediatrician. Things are getting a little bit more complicated. My wife has gotten hung up outside the home. So we're going to go do that. And then I will come back and try to get you guys a little extra recording tonight. I know that this is slightly messy, and I apologize that it ate up today's office hour. If you're trying to get a hold of me in office hours, I'll do an extra one a little bit later in this week. I hope you guys have a good rest of your day, and I will see you at the latest on Wednesday.